Hi everyone, myself Aishwarya GS 4MS20 MCS61 from Maharaja Institute of Technology, Mysore. I am here to explain about the benchmarking of a stochastic production planning in a simulation testbed. Here, firstly we describe what is stochastic production planning. It mainly describes for a system with random lead times and its requirements. The stochastic production planning, that is SPP, is a linear program that determines quantities of products to release into production in each time period that provide the desired quality of service at a minimum cost. We also illustrate how an advanced planning procedure like the SPP model can be integrated into discrete event simulation model to facilitate better understanding and to manufacture the supply chain networks. First one is stochastic production planning model. This production requirements for the system are represented by the cumulative requirement RIT of product I required in periods of up to 1 to T. These requirements may be deterministic values or random variables with specified distribution based on the sales forecast, management decisions, or other information. Lead time and expected outputs. The lead times to produce parts in the manufacturing facility or network depend on the network structure, protocols, machine scheduling rules, etc. We assume that the lead time for type I products are independent random variables with a specified production probability distribution. Fi of t. These distributions may be estimated from production data or other system information. Such a single stage lead time may actually represent the time for several production stages or tasks in a multi station production network. The lead times determine the output process. The initial work in progress WIP in the system also contributes to the output process. It follows that the expected cumulative output for product I in periods up to 1 to T is given by the equation where the first sum is the expected output from the WIP at time 0 and the second sum is the expected output from the quantities released up to period T. Next one, to determine the costs. We consider three costs associated with each product I in period T. First one is a late cost, that is CIT, for each unit of product I that is backlogged in period T. And second one is an early cost hit for holding a finished unit in inventory. Third one is an in transit cost hedge. It for a unit that is being processed. In selecting release quantities, one aim is to minimize the sum of these system costs. The objective function we will use in this regard is here the first line is an approximation for the expected uh, early cost, which is CIT E of RIT minus YIT plus H of IT E of RIT minus YIT, where YIT is the random cumulative output of product I up to period T. The first line is a linear function of the input quantities, but the expected late plus early cost is a nonlinear function of the inputs. The term on the last line is the expected WIP of product I being processed in the period T. The input up to time T minus the cumulated expected output. Next one is to determine the quality of service. To determine optimal quantities XIT to release into the system, trade-offs between early and late costs are one consideration. In addition, manufacturers often want to guarantee a certain quality of service for its customers to the effect that deliveries to them will be on time with a high probability. This QoS is often, that is quality of service, is often given a higher priority than reducing holding costs, since long run customer satisfaction usually affects more profits than the holding costs do. do. For our system, the QS criteria is to ensure that the cumulative quantity of product I delivered by each period T meets the requirements RIT with a specified QoS probability. In other words, QoS criterion is where YIT denotes the random quantity of product I delivered by period T, and YIT has a mean given by equation 1. To convert this stochastic constraint into a linear constraint involving only expectation, the cumulative output YIT is modeled as a position random variable. Next one is the auxiliary constraints. The last feature of the production system are auxiliary constraints related to resources, personnel, scheduling, etc. that affect the production flows. The SPP model can contain constraints that are linear functions of the release quantities XIT. For illustrative purposes, we will include the constraints here. This ensures a smoother production loading by bounding the difference between release quantities in adjacent periods. And the linear capacity constraints can also be incorporated to reflect manufacturing capacity, resource capacity, or WIP constraints. Next one is the LP optimization. This subsection describes SPP as a linear program for optimizing the release quantities for the production system described in the preceding section. The general aim is to find optimal release quantities XIT that minimize the system cost function subject to the quality of service constraints and the production smoothing constraints. The LP above provides a static optimization of the release quantities for a fixed planning horizon. To use the model in a simulation for actual production planning over a series of time periods, one would run the LP in each time period with updated information as described. For the system described, the general aim is to find optimal release quantities. Next one is the implementation of the model. To represent demand-driven production environments, incorporating APS procedures in DES is a practical way of translating customer demand into feasible input rates. This section describes how SPP model is formulated as an LP in the previous section would be used to generate production plans for a series of time periods in a simulation. At the beginning of each time period, the system would perform the following steps. First one, to observe the production output from the previous period and the current WIP quantities at WI0 of K. Update the requirements for the next T time previous based on new demand forecast and the previous period output. That is to increase or decrease future requirements by backlog products or extra finished products respectively from previous period. In the previous slide, the diagram represents to run the LP with the current WIP and updated requirements for the new time horizon to obtain optimal release quantities XIT. Release the quantities XI1 into the system for the current production period, that is the optimal quantities XIT for periods T greater than or equal to 2 and forecasts or future release quantities. This procedure would yield production release times generated one period at a time. At the beginning of each simulated period, incorporating SPP in a DES model facilitates more realistic representation of supply chain models and dynamics and enables better evaluations of alternative production or supply chain strategies. That figure illustrates how this rolling horizon SPP procedure can be incorporated with a conventional simulation model to extend the traditional scope of simulation studies. As SPP explicitly accounts for the stochastic nature of demand and lead times, DES is a practical approach to test its performance. In section 5, SPP is generated with the DES model like above to test its performance against two other planning procedures. Next one is a comparison with MRP type control policies. To access the quality of SPP model, we compare it with two alternative planning models. First one is a classical MRP model and a myopic requirements planning model, that is MYRP model. This section describes these models. We consider a classic MRP model that generates production plans and plans under the assumption that for each type I product, the lead time is a specified non-random constraints Li measured in terms of time periods, and its requirements RIT are not random. The general MRP philosophy is to release quantities in each period that would cover the requirements in the next Li periods. For simplicity, assume there are no auxiliary constraints on the release quantities. Specifically, at the beginning of each time period, the system would perform the following steps for each type I product. First one, to observe the production output from the previous period and the current WIP quantities, WI of K. Update the requirements based on new demand forecasts and the previous period output. That is to increase or decrease future requirements by backlog products or extra finished products respectively from previous period. To release the quantities Xi1 into the system for the current production period, although this model generates the production plans dynamically, the release quantities do not depend on costs or QoS. That recognize there are production uncertainties might choose conservative lead times to try to ensure that requirements are satisfied on time with a high probability. For instance, one might set the lead time constant to be Li equals mu plus sigma when one believes the lead time to be a random variable with mean mu and the standard deviation sigma. However, conservative lead times result in a higher holding costs for finished products. We also compare the SPP model with a myopic requirements planning model. We briefly describe the model here. For a more detailed description, the MYRP model is a one period look ahead model where at the beginning of each period the WIP and next period requirements are observed and a manager releases enough products to meet the requirements with a desired probability. In overall, the MYRP would operate as follows. At the beginning of each time period, the system would perform the following steps to find each product I. First one is to observe the production output from the previous period and the current WIP quantities WI of K. Determine the requirements RI1 for the next period based on demand forecasts and the previous period output. That is to increase or decrease the old requirements by backlog products or extra finished products respectively from previous period. Release the quantities Xi1 into the system for the current production period where Xi1 is the smallest quantity that satisfies. The prime consideration here is the QoS constraint. The lead time distribution is used in a limited way for a one period look ahead. In contrast, the MRP model does not use the lead time distribution but implicitly attempts to satisfy the QoS by infanting the lead time. Neither model uses costs to determine release quantities. Next one is a simulation study. In order to evaluate the SPP procedure with the two other MRP-like control policies in an integrated simulation environment, a simulation model of a manufacturing network shown in the figure was constructed. As the focus is on high-level planning, we use a single-stage lead time distribution to represent the time for several production stages in the multi-station production network. To implement the SPP procedure, the simulation model is interfaced with an optimization software MOSEK to solve the LP model for each period as shown in the figure. At the start of each time period of the simulation, the LP is solved for the optimal release quantities for the next t time periods based on the observed output of the previous period. It also illustrates how the MRP and MYRP models are integrated with the simulation model. The performance measure used for the comparison is the total average cost, which includes the late costs, early costs, and in transit costs for operating under each model policy. We simulate the operations of the manufacturing network under three planning models for a single product over T is equal to 50 time periods. For each simulation scenario, we can run 50 replications. For each time period, we simulated the completion time of the release time quantities determined by the lead time and the residual lead time distribution. A common lead time distribution assumption used in the normal distribution. To minimize distortions from initial settings like the initial WIP, we consider the first 20 periods and only collected data on costs and observe QoS for the last 30 periods. And also, we first study the characteristics of the SPP model for various cost ratios and QoS levels. Uh, we study the release patterns for three models SPP, MRP, and MYRP and compare the total average costs of the operating under each model. Next one is the simulation results for SPP model. The operation of the manufacturing network was simulated with the SPP planning procedure for a variety of cost ratios and the lead time distribution. This figure shows the overall release quantities under the SPP procedure with various cost ratios for the different lead time distribution when the QoS level is at 0.67. This level corresponds to meeting the requirements at least two-thirds of the time. The release quantities are higher when the late costs are high and lower when the early costs are high for the normal distributed lead times. This is intuitive as more is released when the late penalty cost is high and less is released when it is expensive to be early. The release quantities for the discrete distribution are similar for the various cost ratios. As the optimality of the solution to the LP can be only be affected when the cost coefficients or production rates are changed. In the case of the discrete lead time, the range of variation of the costs are still insufficient to change the optimal solution at each period to a different extreme point of the solution phase. This indicates that in certain situations, the quality of service constraints are more crucial in determining the release quantities than costs. That figure plots the average cumulative release quantities for equal cost with varying QoS levels for the discrete lead time distribution. As expected, the average release quantities increase as the QoS level increases. Similar trends are seen for the normal 2,1 and normal 5,3 lead time distribution in the graph. Next one in the simulation results for SPP, MRP and MYRP models. To compare the pattern of releases, figure 6, 7 and 8 show the cumulative release quantity graphs for a single simulation run for the SPP model with equal costs. The classical MRP model and the MYRP model when the QoS level is set as 0.67. For the classical MRP model, the lead time is set to constant, that is mu plus 1 for the normal distributed lead times. This corresponds approximately to the 71st and the 84th percentile of the normal 5,3 and normal 2,1 lead time distribution respectively. For the user defined lead time, the MRP lead time is set equal to 3. This corresponds to the 70th percentile of the lead time distribution. Figure 5 describes the discrete lead time, the average cumulative release quantities for period of 50 for equal cost at different QoS level. And the figure 7 describes the normal 2,1 lead time, cumulative release quantity for SPP model, MRP model, and MYRP model where QoS is equal to 0.67. Figure 6 describes discrete lead time for the cumulative release quantity for SPP model, MRP model, and MYRP model where QoS is equal to 0.67. And last, the figure 8 describes the normal 5,3 lead time, cumulative release quantity for SPP model, MRP model, and MYRP model where QoS is equal to 0.67. The cumulative release quantities are smoother for the SPP model as compared to the MYRP model. The MYRP model does not account for the requirements for later periods and experiences large surges in release quantities when the WIP becomes insufficient to fulfill the requirements. To release quantities for the MRP model is parallel to the requirements but shifted back to account for the constant lead time and initial WIP in system. Next, we observe the total average cost for various models. Table 1 shows the relative costs of the SPP model with respect to the MRP and MYRP models for different QoS level. The SPP model has a much lower expected cost than the MYRP model, at least 25% less than the MYRP model for different distributions, and QoS levels are considered. This is because the SPP plan holds less finished inventory and WIP. The cost for the MRP model is comparable to the cost of SPP model for discrete distribution, where the lead time and variance is small. For the normal distributed lead times, the expected cost from the SPP plans is at least 10% less than the MRP plans. As an average, lead times and variances become larger. Without accounting for the uncertainty in the lead times, the cost for the MRP model becomes higher. From the experiments conducted, we see that the SPP model outperforms the MYRP model in terms of cost. The release for the SPP model are smoother than the releases of the MYRP model. The SPP model has a cost advantage over the classical MRP model as the lead times become larger and more uncertain as it is more adapted to the lead time uncertainties. Finally, conclusion. In this paper or in this seminar, we have described a dynamic stochastic optimization planning model that determines when to release raw materials into a production system or supply chain network. The model is applicable to a variety of systems whose lead time and random variable distribution of which can be estimated under typical operating conditions. As our approach is dynamic, it is flexible to various review policies, customer quality level, and costs. We have provided a procedure for the practical implementation of the model in an extended simulated framework. We have also presented initial simulation results that show that the model is more realistic than MRP models and determines less cost production plans. Future work includes the development of more general SPP models for production networks with a multiple station with several servers, explicitly routing of products and assembly of products. The lead times for these model must be formulated in more detail in terms of these network features and the queuing delays depending on the network loads. Um, Successive approximation procedures can be used to compute lead time distribution in these general cases and applied in the dynamic optimization approach in the same spirit as the current SPP model. Thank you.